All right. So for this one, what we have as our integrand is 1 over x squared minus a squared. You can factor that denominator. It's the difference of two squares, so it's x minus a, x plus a. Right? So again, we have distinct linear factors. So each factor is linear, and they are different from each other. So we want to decompose this into two partial fractions. I'll have a1 over x minus a plus a2 over x plus a. And then the next step is to multiply through the whole equation by that common denominator, which was x minus a times x plus a. So on the on the left-hand side, all that's going to do is eliminate the denominator and just leave me with a 1. And then on the right-hand side, when I distribute it to that first term, the x minus a's will cancel, and I'll be left with a1 times x plus a plus, and when I multiply it by the second term, the x plus a's will cancel. I'll be left with a2 times x minus a. All right, so let's use our little trick now. Instead of expanding this, what can I let x equal? Let's solve for a1 first. So what do I want to let x equal? If I want to keep a1, but I want to eliminate the other factor.
Negative a.
I want to keep a1.
Just a.
Just a. So if I let x equal a, right, that's going to make this term be 0. And I'm going to have 1 equals a1 times 2a. And I can then solve for a1, just divide out the 2a. a1 equals 1 over 2a. Right? And now if I want to solve for a2, we'll do what Catalin said and let x equal negative a. Right? In which case this term becomes 0. And I'm left with 1 equals a2 times negative 2a. And so a2 equals 1 over negative 2a. Whoa. All right. Cool. So now our integral, right? Our integral becomes the equivalent integral, which will be a1 over x minus a, where a1 is 1 over 2a. So I'll have 1 over 2a over x minus a plus negative 1 over 2a over x plus a dx, right? Remember that the lowercase a's are constants, so I can just factor them out, and I can write this as two separate integrals. So I'll have 1 over 2a times the integral of 1 over x minus a dx. I'll just do minus 1 over 2a. It's the integral 1 over x plus a dx. All right, what is the integral? What's the antiderivative of 1 over x minus a? Not everybody all at once. We talked about it yesterday. What's the integral? What if it was just 1 over x? What's the antiderivative of 1 over x?
Natural log of x.
Natural log of absolute value of x, right?
Yeah, sorry.
So remember I said as long as there's not a coefficient on the x and it's just x plus or minus a constant, it's still just going to be that natural log absolute value of whatever is in that denominator, right? And since I have a 1 over 2a in front of both of these, I can just factor it. And again, we can just condense this, so final answer, 1 over 2a, natural log absolute value of x minus a over x plus a. Whoa, plus c. Okay, let's try a new type of problem. What do we do when they're linear factors but not distinct, meaning some are repeated? So in that case, when you break it out into partial fractions, you have to account for what the denominator could be, or what could make the common denominator, I guess. So the generalized version of this is kind of hard to understand, I think. If you look down here at this example, hopefully that'll make it clear, and I'll try and explain why it works this way. So here we have a rational expression. We have repeated linear factors, meaning we have x squared, right? So that's x times x, meaning x is a linear factor, but it's repeated. We have two factors of x, right? We also have repeated factors of x minus 1. So when you decompose this into partial fractions, you have to account for all possibilities that could make up this common denominator. And so what that means is you have to have a constant over x plus a constant over x squared, plus a constant over x minus 1, plus a constant over x minus 1 squared, plus a constant over x minus 1 cubed. And the reason being, there are a bunch of different combinations of these that would still make that common denominator, right? So if I just had these two partial fractions, the common denominator of just those two partial fractions, the b over x squared and the e over x cubed, their common denominator is this. Do you guys agree with that? But it's also true that if I add in this term, the common denominator of those three partial fractions is also this, right? And it's a possibility that I could have a term in this form because those four partial fractions still have that same common denominator of x squared times x minus 1 cubed. And of course, if I add in this partial fraction, all five of those have that same common denominator. So what we're trying to do is account for the possibility that this could decompose into many combinations of these five partial fractions. Now, it may not. It may be the case where when we solve for A, B, C, and D and E, that some of them come out to 0. So it could be the case, for example, that A comes out to equal 0, in which case this term is gone, right? And it could be the case that C comes out to 0 and D comes out to 0. Those two terms are gone. And we're still left with some non-zero constant for B and some non-zero constant for E. And there, we've decomposed it into just those two partial fractions. But it may be the case where A, C, or D are also non-zero. And so we're trying to account for that in our decomposition here, okay? So let's do an example of this. Whoa. All right. So quick reminder, what's the first thing we need to do? So we're trying to integrate a rational expression. It's not simple. We don't just know it off the top of our head. We think we're going to use partial fraction decomposition, but what's the first thing we need to do before we start decomposing it? It's the first thing we need to check for.
You need to see if it's proper or improper.
Is this proper or improper?
Improper.
So we need to do a little polynomial long division. All right, so divisor, x cubed. Oh, I need to give myself more space than that. X cubed minus x squared minus x plus 1 into the dividend, which, remember, I like to put placeholders. I like to make sure if the polynomial decreases by 1 degree each time, so I'm going to do x to the 4th, and then it skips x cubed, so I'm going to do plus 0x cubed, and then minus 2x squared plus 4x plus 1. All right, and then we think, okay, what do we need to multiply x cubed by to make it x to the 4th? The answer to that is just x. So I'm going to take that part of the quotient, I'm going to multiply it back over by the entire divisor. So x times x cubed gives me x to the 4th. Then I'm going to have minus x cubed. I'm going to have minus x squared plus 1. Now we're going to subtract the whole thing. No, plus x, not plus 1. All right, so I get, what, 0, positive x cubed. This is going to be negative x squared plus 3x. And I'll bring down the plus 1. All right, what do I need to multiply x cubed by to get x cubed? And that's just 1. Good. Multiply that by the entire divisor, we'll have x cubed minus x squared minus x plus 1, and we'll subtract the whole thing. We'll get 0, 0, 4x, and 0. All right, so 4x is our remainder. So this is equivalent to x plus 1 plus the remainder, 4x, over the divisor, which was x cubed minus x squared minus x plus 1 dx. All right, well, those first two terms, those are no problem. Those are trivial to find the antiderivative of, right? But we still have this third term that's rational. So we're going to need to decompose that. All right, so the first thing we need to do to that term is to factor the denominator. Do you guys remember how to factor by grouping? It's probably been a solid 2 years since you've had to do that. All right, so here's how we factor by grouping. So you're literally just going to group terms. So I'm going to do x cubed minus x squared. I'm going to do plus negative x plus 1. Okay, so I just grouped two terms. What you want to do is in each set of parentheses, factor out what you can. So in the first set, I can factor out an x squared, and I'm left with x minus 1. And what I want to do is get the second set of parentheses to match that set of parentheses. So I can do that by factoring out a -1, right? And now this will be x minus 1. And now since I have x minus 1 in both these terms, I can factor the x minus 1 out. And that'll leave me with what's left over, which is x squared minus 1, right? And then I can actually factor that even further. X minus 1 and x squared minus 1 will factor to x minus 1, x plus 1. All right, so I have x minus 1 quantity squared. That is a repeated linear factor. I have two factors of x minus 1. And then I have that x plus 1. Right? Okay, and now we're ready to try and decompose this rational expression. So let's go ahead and do that. So I'll do a1. I'll put that over the unique factor. I'll put that over the x plus 1. It doesn't matter what order you do this in either. Like I could have put the first term over x minus 1. And I'll do a2 over x minus 1. And then I have to do a3 over x minus 1 squared. Does that make sense? So I'm accounting for all possible partial fractions that would make up that common denominator on the left, right? Correct? All right. What's the next step?
Multiply out to cancel the whatever the bottom thing is called.
Common denominator?
Is it called the
Denominator.
Yeah, well, I'm gonna add the numerator. Is it called the numerator, the one on the bottom, or the denominator?
The denominator. Oh, boy.
I don't know what it's called. I just know it's the bottom one.
I made everybody in Calc 1, we just did quotient rule. So I made them memorize that dumb rhyme and type it out in the chat. I told them they had to type it out in the chat to me or else they fail my class today. You know what I'm talking about? The low D, high minus high D, low.
Yeah.
All right.
It's not a dumb rhyme. It works if you can.
Yeah, it does work. I just feel dumb when I teach it. All right. So multiply everything by that. On the left-hand side, it cancels the denominator completely, just leaving us with 4x. On the right-hand side, for the first term, it's just going to cancel the x plus 1, so we're going to be left with a1 times x minus 1 squared. The second term, we're left with a2 times x minus 1 times x plus 1. And the last term, we're left with a3 times x plus 1. All right, we can use our little trick to some effectiveness, but I don't think we can use it all the way here. So for example, if I want to solve for a1, what should I let x equal?
-1.
Good. So that's going to make this whole term go to 0. It's going to make this whole term go to 0. And it'll just leave us with -4 equals, what, 4a1? So I'd have -2 and then squaring that, making it 4. All right, so I know that a1 should be -1. Here's the problem. I'm not going to be able to choose anything that will allow me to solve for a2, but eliminate everything else. right? Because if I choose 1, that's still going to eliminate, that'll eliminate the A1 factor, and it'll leave the A3 factor, but it'll also eliminate the A2 factor. Well, let's do that. That'll let us solve for A3, right? So let's let x equal 1. All right, then this term is gone. That goes to 0. This term is gone. That goes to 0. And we're left with 4 equals 2A3. So A3 equals 2. All right, well, we're not able to solve for A2 by eliminating other things, but here's another little trick. We now know the values of A1 and A3, so I can plug those in. So I'll have 4x equals -1 times x minus 1 squared. So I'm just replacing A1 with its value of -1 plus A2 times x minus 1 times x plus 1. And then A3 is 2, so plus 2 times x plus 1, right? Now, I wasn't able to choose any value for x that would let me eliminate the A1 and A3 terms and leave the A2 term. But now all I'm left to solve for is A2, right? And as I said, this is an equation, so it should be equal on both sides no matter what value we choose for x. So why don't we just choose some other value for x that won't eliminate A2 in this case? So give me a value of x that won't eliminate A2.
Zero.
Sure. 0, 100, 3 billion, 47. Any of those would work as long as they don't eliminate A2, right? But yeah, I agree with Eva. 0 is probably the easiest one. That just makes the left-hand side 0. Over here, what are we going to have? -1 plus, oh, I guess minus A2. Plus 2. And then boom, that gives us an easy way to solve for A2. I'm just going to add A2 to the other side. A2 equals 1, right? Okay, well, we're ready to decompose, and I have officially run out of room. I'm just going to go ahead and use this giant gap of blank space. Not great board organization, but I'm coming up here. All right, so now our integral becomes the integral of x plus 1. A1 is -1, so minus 1 over x plus 1. A2 is +1 plus 1 over x minus 1. And then A3 is +2 plus 2 over x minus 1 squared dx. All right, those first 4 terms shouldn't really be an issue for us at this point. We can anti-differentiate them. So we'll have x squared over 2 plus x minus natural log absolute value x plus 1 plus natural log absolute value x minus 1 plus, now this third one, we do have to do a little bit of a use of for. I'm going to pull the 2 out front, and I have 1 over x minus 1 quantity squared dx. Oh, that's a horrific integral. There we go. All right, so for that one, I would let u equal x minus 1. So then du equals dx. And that's going to make my integral 1 over u squared du, which is the integral of u to the negative 2 du. And the antiderivative of that is negative u to the negative 1, which when we replace the u will be negative x minus 1 to the negative 1, right? All right, so final answer. We're going to have x squared over 2 plus x. I'm going to combine those natural logs. You can reverse their order and it would be subtraction, right? So it would be plus natural log of the absolute value of x minus 1 over x plus 1. And then I have the last term that I solved, which is in purple. Remember, I have that 2 out front too, so it's going to be minus 2 over x minus 1. So I just, since it was to the negative first power, I just flipped it to the denominator. Plus c. We did it.
Wait, Mr. Toller,
Yeah.
in like the first line of green, I just can't remember, where did you get like the stuff that you put inside of the integral? What is that from?
So first we did long division and we came up with this, right?
Right.
And then we took this piece, specifically just the rational expression, and we broke it down into partial fractions like here. Right?
Oh yeah, I forgot that we had the x plus 1 originally. I don't know
Right,
where that
right.
come from. I forgot we didn't include that long.
It was a long journey.
Yeah.
Okay. So let's see. I think that's good for today. I think we did a lot of notes. So what I'm going to let you do